Rao Bhim section 7.5 continued. Theorem 7.5.5. In this theorem, we can actually work with any subsets S and T of an inner product space. So we start with an inner product space and any two subsets, not necessarily subspaces. In that case, their perps will have the reverse containment, which is just straightforward, because if I take anything in T perp, suppose I take T some x in T perp, then x is orthogonal to everything in T. In particular, it must be orthogonal to everything in S as well, because S sits inside T, and hence we get this result. You can actually compare this with this result, that if S is contained in T, then S complement will be larger than T complement. The next theorem says that suppose I start with an inner product space and two subspaces S and T. Now I have to work with subspaces. Then S plus T whole perp, the orthogonal complement of S plus T, is same as orthogonal complement of S, intersection orthogonal complement of T. It will be better to visualize this result first before we start proving it. Suppose we are working with R3, V is equal to R3, and the x-axis is S and the y-axis is T, then S plus T is the entire xy plane, that is everything which can be expressed as something in S plus something in T. If I take its orthogonal complement, we know that it has to be the z-axis. Now if I look at this, S perp orthogonal complement of S is this plane, the yz plane. This is our S orthogonal complement, and similarly T orthogonal complement is T perp, which is the xz plane, and if I take the intersection of the two, I am left with only the z-axis. So both sides are equal to the z-axis. Whenever we want to show a result like some set is equal to some other set, basically there's only one technique. You take any arbitrary element here, show it is here, take any arbitrary element here and show it is there. So let's start. Suppose I take any arbitrary element here. So if I take any arbitrary element in the left hand side, I know that it must be orthogonal to everything in S plus T. Now what are the elements of S plus T? They are of the form some little s plus some little t, where S is in S and T is in T. Well, suppose I take T equal to the 0 vector, because since T is a subspace, it must contain the 0 vector. In other words, the entire subspace S is already a subset of S plus T. So in particular, X must be orthogonal to S also. So X must belong to orthogonal complement of S. By the very similar reasoning, I can take this to be 0 and this to be T, in which case X is also orthogonal to every element of T. So X also sits inside orthogonal complement of T. Hence X is in this and this, hence this intersection. So I have proved that the left hand side must be a subset of the right hand side. Now we have to show the containment other way around. Suppose I now take something in the right hand side, say y. Now y is in S perp, which means y is orthogonal to everything in S, and y is also in T perp, so y is orthogonal to everything in T. Now if I take anything in S plus T, it is of the form S plus little t, where S is in S and T is in T. I have to show that y must be orthogonal to S perp T, which means I have to show that ST inner product is 0. But I know because of the distributivity property, this is nothing but this plus this. And just now I said that this is 0 and this is also 0. So the total must be 0. So y must be orthogonal to S plus T as well, which means whatever element you take here, y is perpendicular to that, hence y belongs to the left hand side. Finishing the proof of the other inequality, hence the must be the same. I hope you have noticed that this is very much like the De Morgan result from usual set theory where we have union, and this is usual complement. So A union B whole complement is A complement intersection B complement. That is what is called one of the two De Morgan's laws. Now there is another De Morgan law which says that if I work with union intersection here, then this will be union, and in fact one follows quickly from the other by just taking complement of both sides. So here also we have got its dual version. So I will say S intersection this is actually S plus T part. And how do you prove this? That is pretty simple. You simply remember that S perp and T perp, they are subspaces. So I will apply the first result to this side. So I will start with this and then take whole perp of that. So I will apply this result and I will be left with S orthogonal, orthogonal of that, intersection T, orthogonal, orthogonal of that. Now I quickly recognize that this is nothing but S and this is nothing but T. So I see that S plus T orthogonal is this. Now I take perp of both sides. As a result, I am left with this, because orthogonal cancels off, and I am left with S intersection T whole orthogonal. And that is the second equality. Next, we discuss the very important concept of an orthogonal projection. We start with an inner product space and some subspace, not just a subset, subspace of V. Then inside V, we are having two subspaces, S, the thing we started with, and its orthogonal complement, and we know that this result is true. In fact, we also know that these two things form a direct sum, so sometimes people will write this, meaning that these two things have intersection, just the null vector. Whenever this happens, we can write any vector V in V uniquely as two vectors, this and suppose I call it T. And these S and T are unique. And I call this S vector the orthogonal projection of V onto S. For all V in V, there exists unique S in S and unique T in T such that V can be written as S plus T, and this S is called the orthogonal projection. Because it's unique, I can call it the orthogonal projection of V onto S. Now our book uses the term into S. Well, into is a more general term, but this map we are going to see pretty soon is actually an onto map. So I called it onto S. So it is very important to understand it pictorially. Suppose we are working with R3 and S is the xy plane and here is a vector V, then we already know that its orthogonal complement is the z-axis. Now this vector V is sticking out of the board like this. Then to visualize the orthogonal projection of V onto S, we imagine that light is shining on to S perpendicular to X, so it is like the floor and we are at 12 noon, so sunlight parallelly is shining down like this. And what is the shadow that is cast of this arrow? So this is an object, the shadow that is cast, that is the orthogonal projection of this vector onto S. So S is like the screen and D is like the object, and the sunlight is shining. Since it is sunlight, it is shining parallelly perpendicular to S, hence the term orthogonal projection. Now you must understand that there is a limitation of this visualization. If my vector is under the xy plane, then you have to imagine that sunlight is shining upwards. So basically, I am always taking that component of V which is lying along S. So in this case it will be, if this point is x, y, z, then its orthogonal complement will be, its orthogonal projection onto the xy plane will be x, y, 0. A word of warning here, it is not x, y, it is x, y, 0. So both V as well as its orthogonal complement lies in the same R3. Do not think that its projection onto xy plane is merely xy. Don't forget about the 0. In general, if you are given any S and any vector V, and you want to find the orthogonal projection of V onto S, always think of S as a screen, a plane, though S may not be of dimension 2 in a problem, but that's how you visualize. And this is the origin, and the thing is coming out, the vector of whose projection you are interested in is coming out of the origin like an arrow. You are shining light which is perpendicular to S, and then the shadow that this object casts on the screen, that is the foot of the perpendicular, dropped from the tip of this arrow. So this vector will be the orthogonal projection of V onto S. And you can easily see why I called it onto S, because if I just take my original arrow to be lying already on the screen, then its shadow will coincide with itself. If you are lying flat on the ground, then your body coincides with your shadow. So every vector in S is shadow of something, is shadow of at least of itself. In fact, it is shadow of so many things. If I take this vector, then also I'll have the same shadow. If I take this, then also I'll have the same shadow. As long as all the tip of my arrow lies on the same perpendicular line to S, the shadow is going to be at the same point. So there are, in this case, infinitely many points whose shadow will lie at that point. So keep this picture in mind. When your screen is the xy plane, then it is quite easy to visualize the projection, and also it is easy to get a formula. And the formula is this: if this point is x, y, z, I am writing it as a column vector, this becomes x, y, 0. Now if you think for a moment why this happens, that's quite easy, because you just took the component of this along the, that is lying in the xy plane, which basically means you took the x-axis, you took the y-axis, you looked at the part of this explained by the x-axis, namely x, the part of it explained by the y-axis, namely y, and ignored the part which is explained by the z-axis. In other words, you took these bases E1, E2, E3, which is our usual canonical basis of R3, and you expressed this as a linear combination of this, which was basically x times E1 plus y times E2 plus z times E3. And fortunately for us, the screen that we worked with is completely made up of the E1 and E2 parts, so I merely ignored this part and kept this, and I got the orthogonal projection. We were fortunate because for this nice basis, which is so easy to work with, the first two gave me the screen. But if the screen is in some oblique way, then if I work with this basis, this nice result will not hold. However, it is very easy to generalize this simple situation. This is given by theorem 7.5.8, which I shall write in a form slightly different from what is given in the book. Of course, we start with some inner product space V and some subspace S of V. Then I take some ONB x1 to xk of S. It can be just any orthonormal basis of S. Now I extend it to an orthonormal basis of V by appending xk plus 1 to xn, this red part. This was not given in the theorem as it is stated in the book, but this will make the theorem more useful. The idea is, if now you take any vector V in V and then you just express it as a linear combination of all these, which you can do because it's an orthonormal basis of V, then the part using only x1 to xk will be the orthogonal projection of V onto S, and the part which will be made up of this red part will be the orthogonal projection of V onto S orthogonal. In words, if I consider this, then that is the orthogonal projection of V onto S. Now you might be a bit scared to see this complicated stuff. Don't worry. Remember, it's an orthonormal basis. So if you are expressing V as a linear combination of these, then the coefficient of any xi is given by just the inner product of V with the corresponding basis vector. So these are just my so-called alpha i's. So this part going from 1 to k is the contribution to V of x1 to xk, and this part going from k plus 1 to n is the contribution of the red part. So this is lying in S and this is lying in S pop, and we can easily see that V is sum of these two, because if you add them up you get all the way from 1 to n, that gives you entire V. So it's just immediate. Now it gives you a computational tool by which you can actually compute orthogonal projection of V, of any V onto any subspace. All that you do is take an orthonormal basis of the subspace and you apply this expression. Now observe that if you are interested in only the orthogonal projection of V onto S and not on this, then you can merely leave it at this. You can avoid this extension part and you can define this as V minus whatever you have projected onto S. That must be the perpendicular thing, and that is how the theorem has been stated in the book. They have not given you this line, and here they have written simply, they have called, suppose I call this X, then they call it V minus X, which makes the theorem look shorter, but I think this gives you the entire picture. We shall end this video with a quick computational example not in the book. Suppose I am working with R3 and I give you this particular subspace, which is x equal to y equal to z line, the kind of a diagonal that passes right through this 3-axis, and I want to orthogonally project anything here. So given any vector, I want to drop a perpendicular and I want to find the foot of the perpendicular. Let's see how we can use this theorem to do this. I will first take an orthonormal basis of this. Since it is a one-dimensional thing, my orthonormal basis will consist of any unit vector lying along this. Okay, let's start with any vector lying along this. A simplest example that I can think of it is 1, 1, 1. So this gives me a basis of this subspace. Now I want to turn it into an orthonormal basis. Basically, I will apply Gram-Schmidt process. But since I have only one vector, I will need to do only the first step of the Gram-Schmidt process, which is basically dividing it by its norm, which is root 3. So I get this vector. Now, if someone gives me any vector, suppose that vector is x, y, z, I need to find out its component along this, which is basically nothing but this inner product with this. So I will be taking, so I will call this my V vector according to our notation, and this is my x1 vector. So I will be taking V inner product x1 and multiply that with x1. Of course, I do not need to put a sum here, which means I take inner product of x, y, z with this. So it is 1 over root 3. 1, 1, 1 with this is simply x plus y plus z. And then my x1 vector, so yet another 1 over root 3 x, y, z. So the 2 1 over root 3's give me a 1/3, and now I can easily see it has to be x plus y plus z, then x, y, I'm sorry, I just did it wrongly. It should be 1, 1, 1, it should be 1, 1, 1. So I immediately see that the orthogonal projection of any x, y, z onto this will be of this form, x plus y plus z by 3, 1, 1, 1. So you are basically taking average of all these things in each of the components. This result is quite useful in statistics.